Okay, so people are starting to come in. Good to see you, Patricia. I haven't seen you in ICSI yet.
Yet. To see
Yet.
you.
Okay, we're just going to wait one more minute because I know people are switching between sessions, and we're going to go ahead and get started.
So we have to stick to 5 minutes, right?
Yes. Yeah, I mean, it's only 4 papers, so if you go a little bit, it's okay. It's when it's 6 papers that it gets a little bit complicated, but it's only 4 in this session. So okay. I won't complain too much.
I just added a slide.
I won't complain too much. Okay, just one more minute. Okay. Okay, I think we can go ahead and get started. Welcome everybody to the session on green and sustainable technologies. My name is Grace Lewis from the Carnegie Mellon Software Engineering Institute. And today we have 4 papers. The structure of the session is going to be very similar to everything you've seen so far. Presentations are only 5 minutes long. I'm not going to be super strict because we do only have 4 papers, but obviously at some point I'll say, okay, enough, we got it. But we'll keep our presentations. We'll try to keep them to 5 minutes. I will ask you to obviously please interact with the speakers and ask questions. We're going to do questions in 2 forms. If you don't want to speak up or you can't speak up because you're somewhere you can't, perfectly fine. Enter your question in the chat. Leo and I will be monitoring that. And then I will repeat the question for the speaker. Just make sure you say this question is for this particular speaker. If you would rather speak up, just say I have a question, and now at some point I'll say so and so, please ask your question. But obviously we're open to both forms of interaction. So with that, let's go ahead and get started. So our first presenter is Ilias Gerosatopoulos, and he is going to present his paper on expressing the adaptation intent as a sustainability goal. Go ahead, Ilias.
Thank you, Grace. Can you see my screen? Can you hear me?
Yes.
Oh,
yes.
Great. Thanks a lot for the introduction. Yes, this is a joint work with my colleagues Claudia and Patricia, who is also here, so can also help answer questions if needed. The 2 keywords, main important concepts in this work is adaptation and sustainability. Actually, we are active as a group in both software adaptation and software sustainability, and we thought to merge these 2 worlds. And in this paper, which is a vision paper, we describe, we start from the motivation, which is that the software systems that we develop as being adaptive, so dynamic and being able to change at runtime, are very difficult to essentially evaluate on the long term whether this adaptation or this change at runtime has a positive net effect or a negative net effect. Although we develop very sophisticated such systems, it's very ad hoc the way we basically judge them. It can be, for instance, the number of cases that such a system has recovered from a fault. That might be a metric that we use, or it might be a metric that the number of percentage increase in the performance over time, or the number of user requests it has served, etc. It tends to be very ad hoc and domain-specific metric. Looking at that situation and also thinking about systems that we build in the near future that become adaptive in a much more fundamental way, meaning that we don't only prescribe every change that can happen, but systems themselves would like to basically try out changes in a form of a reinforcement learning loop, try out and learn a model or an action that actually works in a particular situation. We feel that it's now the right point in time to focus on the intent of such a adaptive software system. So our main research question here has been how can we express this important intent of adaptation at design time in order to be able to analyze the effect of adaptation at runtime and over a long period of time. So not being myopic and only look at the short-term effect, but really try to judge the changes the system does to itself over a long period of time. The main novel idea is to express this adaptation intent of a self-adaptive system as the sustainability goal it needs to satisfy. Now, the sustainability goal is a concept that comes from software sustainability research, and it effectively captures the network of quality concerns balanced over time. We feel this is a novel, but also an interesting direction, because this way we can frame better the endurance and long-term success over different sustainability dimensions, as I will mention in a second, of an adaptation solution. So succinctly, our approach is to basically capture features and related concerns, and in the end also metrics to measure those concerns in a form of decision maps, which is a modeling formalism that has been already proposed in our earlier research. And based on those decision maps, in the end, be able to frame the sustainability goal of a self-adaptive system. Just to give you an idea of what is a decision map, a decision map has you can model certain concerns that belong to one of the 4 dimensions of sustainability. So social, technical, environmental, or economic concerns is what you can model, and also features of the system. Again, you can divide those into social, environmental, technical, economic nature features. And then basically when you capture the different features of the system, you can associate, and different concerns, you can associate concerns, features with concerns based on the effects that the feature has on the different concern. And effectively, you can have a concern that is affected by different features. Just let me give you a brief example. We have used this to model the adaptation logic of a self-adaptive system called Delta IoT. That's an IoT system, which basically, from the perspective of adaptability, runtime adaptation, it has 2 features: transmission configuration and network configuration. Okay, they are both technical concerns, technical features, sorry. That's why the blue background. And they influence, for instance, transmission configuration influences positively the reliability, which is measured by packet loss in this particular system, but also influences negatively energy consumption. That is because when you increase the transmission of a mode, then basically you consume more energy, but you can essentially be more reliable in your packet sending. And so on. We have to capture all the features and all the concerns, and then we can look at the concerns and frame the sustainability goal by, for each concern, either maximizing or minimizing or ensuring that the concern remains stable over one boundary. Okay, so this is what we did. We tried it in 2 systems so far from the self-adaptation domain. We feel that decision maps is a good starting point for understanding those trade-offs between the concerns that need to be balanced by a self-adaptive system at runtime in order to have a sustainable operation. Of course, there are many more steps here. Our overall goal is to be able to put this into a method or methodology for developing self-adaptive systems. But we need to, for instance, quantify the sustainability goal by assigning weights to each concern. And we can create also adaptation boundaries that the system can be safely in by basically having best and worst case scenarios. So yeah, future plans, we would like to basically identify the different concerns that, and maybe even create a library or some guidelines to help people really create those decision maps and better frame the sustainability of their systems. Also, we want to identify and create some catalogs of metrics related to concerns and provide some. We have started already providing some to work on the tool support for creating the decision maps and evaluating the sustainability of systems at runtime via monitoring. Yeah, and we would be looking for, of course, applying our approach in more and bigger systems. Thank you.
Thank you very much, Ilias. Interesting work as usual. Okay, our second presenter, Rohit, if you can please start sharing your screen. Okay, so our second presenter today is Rohit Mehra, and he is joining us from Accenture Labs. Go ahead.
Thank you so much. Good day, everyone. I'm Rohit Mehra. I'm a senior researcher at Accenture Labs. And today I'll be discussing with you a paper which basically highlights the challenges that restrict the adoption of sustainable practices in the industry. In this case, we refer to sustainability as the energy efficiency of our software system. So that's what we mostly focus on. All right. So ICT, or Information Communication Technology Industry, as we call it. Now, did we all know that ICT industry currently accounts for about 2% of the global greenhouse gas emissions? Now, a major chunk of this can definitely be attributed to the design, development, and distribution of software systems and the massive hardware infrastructure like data centers, networks, clouds required to run these software systems. So, just to give an example, just the Bitcoin blockchain out there consumes more electricity in an year than the entire country of Argentina, with a massive population of 40 million people. And this is just one blockchain out there. Thousands of others also exist. And according to estimates, this is going to grow to 14% of the global greenhouse gas emissions by 2040. A massive jump over in the next 20 years if nothing done to control this. Now, though the concept of software sustainability has existed for a while, but its industry adoption is still very limited. For example, as per multiple studies, developers focus more on software aspects like code quality, performance, reliability, bug resolution, collaboration, but optimizing software systems for sustainability is often neglected. Now, we do have a point of view of why this is the case and why the industry, and certainly in most cases, even academia, is not focusing on adopting sustainable software design practices. Now, lack of awareness is the one to begin with. Now, I remember when I was in the university, we had courses focusing on code quality, code performance, system design, but none on software sustainability. Neither courses like that exist in the open domain out there. Now, imagine that I am a project manager at a firm and I want to incorporate sustainability practices into my project, but I have zero idea as to where to actually begin. Also, most of the current approaches are very intrusive in nature. They need access to your code base, deployment infrastructure, project artifacts, runtime environments in order to suggest optimizations. And unfortunately, in industry, it is very hard to give all that access due to multiple security, compliance, and privacy related protocols that we need to adhere with. And that is especially complicated in a software services organization like us, where all of these artifacts are predominantly owned by the client. Moreover, as a project manager, even if I come across certain tools to suggest sustainability optimizations, most of the tools and approaches work in silos. Just to give an example, so tools to detect unoptimized design patterns in my code, or say energy hogging design patterns in my code. Now, even if this tool suggests removing a specific design pattern in order to improve sustainability, that might have a negative impact on other aspects of the software system, like maintainability or reliability or even readability. Now, there was a specific reason that this design pattern was introduced in the first place in my software system. So, for most approaches, respective trade offs are rarely considered. There is also a dearth of novel green metrics, if I can call it overall. While plenty of matrices exist for determining performance and quality of a software system, even cost, effort, software developers are very unaware of even basic sustainability metrics, like say typically like even CO2 equivalents. Moreover, there are no metrics that allow a practitioner to gauge the overall sustainability of a software project even before beginning that project. Say, for example, how much it will impact my project sustainability if I chose a white background color for my mobile application versus a darker color. And finally, all of this impact is hidden from the developers. While developers can visualize the speed of the code to know about the performance, they can't really see the carbon emissions to realize its impact on the planet, and hence are usually unaware of the negative impact their code is making on the environment. So maybe one such scenario would be retraining your machine learning models again and again, which are again very energy hungry. Now, to overcome some of these challenges, we at Accenture Labs are working on an approach called the Project Green Quotient, which is a non-intrusive questionnaire-based approach that allows a project SME to gauge the overall greenness of a software project at the very beginning by answering about a set of about 50 questions that we have as of now. Again, pertaining to multiple categories like technology, team, process. So again, we are not just focusing on the technology stack related aspects of things or the code related aspects, but a more holistic overview of the entire project. Now, this allows the SME to figure out the sustainability impact of his design decisions even before starting the project, and eventually acting as the first step in his journey towards sustainability. Recently, we have been conducting test pilots of this approach across our organization, and the initial results have been very promising. So, in summary, let's try to be cognizant and be more responsible in the way we design and develop software systems, so that it does not end up harming the planet more than doing good. That's all from my end. Thank you guys for listening to my talk.
Thank you very much. Very interesting. Okay, and let's go then to the third. Oh, questions are starting to come in. That's exciting. Let's go to our third presentation. Stefanos, if you could please start sharing your screen.
Can you hear me?
Yes, we can hear you. So our third talk is Stefanos Georgiou. This is work that he did while he was at Queen's University in Canada. Go ahead, please.
Hi all, this is Stefanos Georgiou, and today I would like to present to you the study I have prepared with my colleagues. In this study, we compare deep learning frameworks with respect to their energy and runtime performance, and we try to point out which are the more energy and runtime performance efficient for training deep learning models. The reason why such study is important is because a huge amount of energy is being used on a daily basis to train models. Different deep learning frameworks can output different energy and runtime performance as well, and we would like to know how much is this difference. Moreover, with this study, we can suggest which framework to use for specific cases. Specifically, in this study, we aim to investigate the following research questions. We want to identify which is the most energy and runtime performance efficient framework for our models, how much accuracy is being sacrificed to have energy and runtime performance efficiency, and which are the most demanding API calls for the corresponding frameworks. To do that, we use 6 models coming from 3 distinct categories. From this study, we also used the NVIDIA's publicly available repository named Deep Learning Examples. Although we have selected only 6 models implemented in 2 frameworks, which are the TensorFlow and PyTorch, since these are the publicly used and according to research studies, it took us more than a month to collect our data. We have 3 categories named recommender systems, natural language processing, and computer vision. To collect our measurements, we used Perf command line tool and NVIDIA's SMI. Moreover, we built a framework named PRENGDL that is publicly available on GitHub, but works only on Debian-based systems that are equipped with NVIDIA GPUs. For our first research question, we find that for training models, TensorFlow is well established for computer vision and recommender systems tasks, while PyTorch performs better for natural language processing tasks regarding energy and runtime performance. For models inference, we find that TensorFlow is more efficient for recommender system and one of the tasks under the computer vision, which is the ResNet 50, while PyTorch for the remaining. But overall, TensorFlow is more energy efficient and runtime performance efficient for training the selected models. For the second research question, our results suggest that energy and runtime performance efficiency for the models are more accurate also. So the models that achieve better performance and energy are also more accurate in most of the cases. However, we only used one set of hyperparameters, and we do not know for sure how different hyperparameters will affect our results. And definitely there is more investigation to be done in the future for this research question. For the last research question, we profiled the call graphs of our programs using the C profile written in Python. After collecting the functions that are responsible for taking the most of the time while training and inferencing a model, we performed a manual analysis to figure out the reasons why they are inefficient. Therefore, me and the second author went through the code and manually pointed out some reasons that may impact the performance of these frameworks. And we discussed this until we reach a conclusion. Also, we find like both TensorFlow and PyTorch suffer from specific API call, which are more costly than others, like PyTorch auto-grant backwards, for example. In general, the study raises awareness on the fact that different deep learning frameworks require different energy runtime performance for the training and inference phases. Moreover, no framework is best for all the selected tasks, and this fact calls for actions to allow users to consider and understand energy runtime performance requirements when selecting a deep learning framework. The deficiencies we found in the current documentation of deep learning frameworks reveal the need of a new green-aware documentation for deep learning frameworks and a way to benchmark the API calls as well in order to raise energy awareness. Also, testing a small model regarding its energy consumption before running a large-scale experiment and profiling to estimate the resource usage can help in selecting the most energy-friendly solutions. That's all from me. Thank you for your attention.
Very much, Stefanos. Very interesting.
Thank you.
Let's go to our last speaker in this session. Timur, if you could put up your slides.
Yep.
Okay. And our last presentation in this session is called EFLECT, Porting and Energy Aware Applications to Shared Environments. And our presenter is Timur Babakol from sunny Binghamton. Go ahead.
Yep. I'm Timur. So I'm going to be presenting our work from SUNY Binghamton on EFLECT, which is a virtualization framework to port energy-aware applications to shared environments. So just as some background, an energy-aware application is some application that has knowledge of their energy consumption. So this kind of feature is really important for green software engineering because then applications can do things like adaptive software design, where they adjust for some SLA, energy testing and debugging, similar to like the traditional performance profiling we do, or energy-oriented approximation. So trying to optimize a system for some energy value instead of just the pure performance value. So the reason, the challenge we were looking at was trying to scale this energy awareness to a shared environment. And the reason for this is that almost all modern systems are built on top of some shared environment. If you consider like hardware systems or software systems, all of them use some sort of sharing system, usually some variation of the Unix time sharing system. And so we want to have a situation where applications are actually aware of exactly what they're doing on the system. The problem that comes up is that in a shared environment, an application is entangled with other applications running in terms of their energy consumption. So you may take a profile on your development system in isolation, but then when you move to the shared environment, it may actually see the energy consumption of other applications, because usually these components are reported from hardware or from some system level value. So what we're trying to do is essentially be able to port an energy aware application so that the development environment and the deployment environment are the same. And so that a developer has confidence that the measurements they take in isolation can be used in deployment or production. So our solution that I'm going to present is EFLECT, which tries to use energy virtualization to avoid energy entanglement. So two of the goals of EFLECT is that it's a pure application layer solution, application level solution. So there's no modifications being done to the operating system. And second, it's customizable. So the system is built to extend to other kinds of energy sources and other kinds of systems. So as I said, the key idea that we're looking at is energy virtualization. So we want to just deliver a slice of energy to the application of what it actually consumed. The way we achieve this is that we actually have whole stack awareness for EFLECT. So it will sample components across the entire system and end up trying to detangle the energy consumption. So in particular, what we want to look at for most systems, for like a CPU server system, we want to know the system's energy, the system's activity, and the thread activity, because threads typically are the concurrency unit, which most of these systems work in. If you think of the Unix system, it works with processes and tasks, where tasks are threads essentially. So we let EFLECT worry about the whole stack, and so the end user doesn't have to. They're just getting some energy signal. So an example construction for this is that you have some thread executing on some computational socket that consumes some amount of energy. So we can just take a pretty simple ratio in order to compute how much energy did the application itself consume at this sample. So the goals we're trying to solve with this is that with eFlect is, one, we have a fine-grained temporal detanglement. So our attribution of energy actually is happening online at millisecond intervals. We're also getting a spatial detanglement because we're aware of which location a thread is executing on if you have a multi-socket system where there can be many CPUs that have different energy readings. eFlect is also decentralized. So if you have multiple applications co-running, each of them have their own eFlect instance and they don't coordinate at all. They're completely independent of each other. As I mentioned, this is a lightweight solution, so there's no OS, VM, hardware modification. Nothing needs to be changed about your runtime. And finally, it's customizable. There's a public API so that we can try to extend it to other systems. Finally, a little bit of information about the implementation evaluation, because I'm going to be presenting that next. We implemented this on the Hotspot JVM for Java server applications. We evaluated against Decapo as well as a Inception version 3 inference session in TensorFlow and Java. For our actual data we collect, we use the Intel RAPL running average power limiting system to get the hardware's energy from the CPUs. And we use Linux's Jiffy system reported by the proc pseudofile system to get the hardware's activity as well as the thread activity. All of these are on machine are conducted on a machine with 40 cores over 2 sockets, so 20 and 20, and 64 gigabytes of RAM. So first, this is an energy share plot for 2 co-running instances of the ray tracer Sunflow. What this plot is showing is that the green line is the energy consumed by a single instance of Sunflow as reported by eFlect, and the red line is the stacked between the first and second instance. And so what we can actually see here is that these 2 separate instances of eFlect, when reported and compared to each other, do actually report that the whole system is consuming all of the energy. In this particular case, for the workflow for Sunflow, both Sunflow instances are trying to maximize utilization of the CPU. They maximize their threads for the number of CPUs. So we actually have 80 threads all competing for essentially 2 CPUs over some number of sockets. And so eFlect, even under that, is still reporting that it's dividing the energy up somewhat equally. Next, I have the same kind of energy share plot, this time for TensorFlow. Just because of the lines, it might be a little bit difficult to tell, but you can see that on socket 1, the first instance consumes all of the energy, more or less, while in socket 2, the second instance consumes almost all of it, if you can kind of see the green lines here. In this case, TensorFlow is not maximizing the number of threads. It has some set number of threads doing work on, and so both instances of the program find some location that they can essentially monopolize themselves. Finally, I have co-running 5 instances of Sunflow, where the idea is to try to see, can eFlect maintain its virtualization as we scale up to a very large number of applications? And so even in this case, when we have 5 instances of Sunflow, which we know is a very, very CPU-intensive application, eFlect is still managing to maintain an attribution that does not exceed what the system is reporting. So finally, I have 2 case studies that I'd like to present. So the first one is for energy adaptation. So as I mentioned, you have some energy SLA that you're trying to target and maintain. In this case, for the adaptation we did, we used Aeneas, which is a stochastic optimizer that, again, targets some energy SLA and tries to maintain it for some configuration space. So in the case where we don't use eFlect, we actually see that the adaptation is pretty slow. So in the top plot, this is an application run in isolation over with Aeneas, trying to optimize it for around a 35 joule SLA. In the bottom one, this is run in a shared environment, co-running with other instances of the same application. And in the initial steps of the optimizer, it actually is having trouble figuring out the proper configurations and makes a huge overestimate and has trouble converging. When we then instead use eFlect, we can see that the system has a much smaller slice of the energy and actually converges very quickly because it's not actually observing the energy consumed by the other applications. My second case study is for energy profiling. So we used a concurrency-aware energy profiler called CHAPI to assign essentially energy to methods and to get a ranking of how much energy, how the top ranking methods for some profile. So here, again, we're looking at CHAPI without eFlect. This is with a database application, the database application H2. So run in isolation. You can see that the difference between the isolated and shared environment is that the second and third methods are not stable. They've actually swapped as we moved into the shared environment. When we add eFlect in, then we actually see that these two methods come back in line and become stable at the topmost methods again. So to wrap up in my conclusion, eFlect is a portability solution for energy-aware applications. It's designed as a black box solution so that the virtualization does whole stack monitoring and the client interface just gets the information about its own energy consumption. And it's lightweight and it is effective. It doesn't require any modifications to the underlying system, and it's precise, scalable, and has low overhead as other data that we have presented in our paper. And that's all I have. Thank you very much.
Okay. So now we will open up our Q&A session. I know that the first question was for Rohit, and I know that he already answered it in text. But what I'm going to do is, just in case people are just listening, which could be feasible, I'm going to read Stefanos's question again, and Timur, if you could just provide maybe a more elaborate answer, given that you're not writing, you'll be speaking. So Stefanos asked Rohit, for the green quotient, do you consider also the system you will run the application? Please feel free to elaborate on that.
Yeah, so Stefanos, as like we already discussed on chat, we do consider the underlying hardware for that particular application. And again, the intent is that, say, if an application can run on, say, 4 cores, 4 GB of RAM, then there's really no need to buy a bigger bare metal server with 200 gigabytes of RAM, multiple number of cores, and multiple number of vCPUs. That is like an overkill for your particular application. And that would be in our particular green quotient, that would be rated negative. And then that would be a sustainability recommendation that will be given to you, that in case you are doing this, then probably tone down your server, or get a lower end server, lower end virtual machine, so that your application still functions in the same way but consumes much lower energy. So yeah, that is taken into account.
Mm-hmm.
Okay. Also, let's consider if you give a set of applications like tools that you're going to use, right? And you have a rough estimation. I guess you have to recalculate this every time, because if versions are changing of the applications that you are using, maybe at some point one tool was using eager evaluation instead of lazy evaluation. So this can change. So I guess you have to recalculate every time.
Yes. So that is why in green quotient we follow a case of a temporal analysis, wherein say every month or every 2 months the evaluation is taken again. So if anything changes in your software application, if anything new you added to your design specification to your application, that is then considered in that next iteration. And then overall, over a period of time, the idea is that your green quotient technically should be in a decreasing trend as compared to when you started working on that application. So yeah, that works in that temporal behavior.
Mm-hmm. Okay. Thank you very much. And Timur, this was a question about making your code available.
So our code has an artifact. There is a public repo as well as an artifact for it. I can share the link in this chat if that's okay. I don't know.
I think that would be great. I think that would be great. Thank you.
Yeah. So
okay.
Oops, I sent it as a question. Sorry about that.
Yeah. No, that's fine. That's great. Patricia, since I know that I have you here, can you go ahead and ask your question, please? It's also for Timur.
Yes, thank you. Now, I was wondering, I found the work very interesting. I was wondering if you have a virtualization commercial platform like virtual machines or containers from VMware. How could you apply your approach to estimate the energy consumption of individual application within a virtual machine or a container? And so if there is possible, and eventually to this end, the limitations.
So there is actually a framework written in Rust called Scafandry that does energy monitoring, that is targeting specifically containerization and looking at containers. They use the same data that we do. Even within a Docker image itself, you can read RAPL, you can read the MSRs. And in fact, case in point, the artifact we use and the previous work we've done have been run in Docker containers and reported energy profiles. So it does work. It can work for these systems and be ported to virtualization systems, as far as I can tell, and as far as I've seen from other people working on these on similar problems.
Yeah. Yes. Thank you.
Okay. Thank you very much. So Tushar, you have a question for Ilyas?
Yes, I hope you can. Okay. So the question, first of all, it's a very good work, and I really like the idea of capturing the intent at design time, and especially for sustainability goals. So congratulations, first of all. The question is related with the how part. So the decision maps are capturing the intent, and I saw the paper also, so there are two case studies as well. But would you like to shed some light on how these decision maps will be translated, or let's say translated into specific or concrete software engineering practices?
Yes, thanks. So what you can do with the decision map is that you can specify at a rather abstract level what you would like to basically be able to monitor. Of course, you have to be able to have the right monitors in place in order to quantify its concern, right? And you have to also have the right metrics to quantify its concern, and then build up the sustainability satisfaction, let's say, percentage, if you want, and basically being able to do that over time. So it is. So there are some parts of the story that can be automated, of course. So we could, depending on the situation, create some and the metric, create some monitors, for instance. Looking at other works, for instance, when we're deploying virtual environments or not, when we want to monitor, for example, the energy, or we want to model, for example, application level concerns. All of this have to come in place. But we're actually working on on basically creating a first prototype where it's based on time series databases, and we're essentially trying to create metrics for its concern, and also map the decision map itself into a calculated weighted average. So what I actually described, we are currently working also with a student of mine in basically having some robust monitoring infrastructure that can always kind of tell you the heartbeat in terms of sustainability, right? But of course, it's not a trivial thing to do. Depending on the metric, it might be pretty complicated, actually. Also, given what Timur was explaining, right? So it's not
definitely that's the case, and it's not trivial, and that's why many. I mean, it has not been done yet, and that's why it is interesting.
As an idea seems straightforward. Taking it really to fruition, it's something that it is kind of the holy grail, if you want, of smart systems that want to have some self-awareness. It is a very kind of nice thing to work on, but it's not straightforward how to solve all the challenges. Yes.
Yeah. One follow-up clarification.
Yeah.
So you mentioned that it is a design time specification of intent.
Yeah.
So I was wondering why design time? Why not we can change this specification at runtime?
Well, I think that by definition it's design time, because you have some humans have to be in the loop when creating the specification, right?
No, I'm assuming that you will have some sort of a interpreter at the runtime. When for monitoring, for example. So when it is in place, it is more or less, it's like a domain-specific language that you are specifying.
I see.
So you can probably have the same, you can use the configuration and the domain-specific language at the runtime as well, because we probably realize or understand that the same application may run in different contexts, and some people or some organization may have different sustainability goals. So I'm just wondering. This is not really a question. It is just.
No, it's a valid point. So maybe Patricia has also some thoughts,
Yes.
thoughts to share on this one.
Sure.
Just a quick reaction from my side. Patricia tends to influence me too much with your answer, so I will try to answer without being influenced. So look, what I believe is the following. Indeed, there is a design time element to this work for sure, right? Because you need to basically sit down with the stakeholders and decide, as you would do with, as hopefully more and more companies will do, to set your sustainability, let's say, practice, right, and goal, and how to reach that. Now you have to do the same for your software system if you want your software system to evolve over time, right? So you have to give the guardrails, and that you can do as a human, right? Now, if you want to have another system giving guardrails to systems, okay, that's an interesting idea, but that's too far. It's like having a robot kind of getting on the elevator, right? But yes, this is the design time, and of course, essentially going kind of the whole loop, the whole let's say, doing the whole thing from design to runtime. This of course makes things harder, because even harder than just looking at the technical issue at runtime, which can be hard enough. But really talking to the stakeholders, getting the requirements right, and then setting up the goals, and then encoding those goals and preserving those goals at runtime. This is the whole picture of what we will try to explain. Maybe Patricia wants to add something.
No, that's an excellent answer. I wanted to point out two things for the design time. The decision maps and the toolkit that I shared in the chat, they have been explicitly indeed created to allow for reasoning and decision making, and translate indeed the sustainability quality concerns in the decision maps into quality attributes and metrics to help and to deduce from there the formula for the indicators for the sustainability goals. So you basically build systematically the whole change from the view towards the measurement plan. But the runtime part indeed is work in progress and is the other side of the coin. For example, to address specifically the domain of cloud-based systems, at the moment we have a visiting researcher in collaboration with the University of L'Aquila in Italy, and he is expert indeed in domain-specific languages, and we are investigating how we can then translate indeed into domain-specific languages and see what is also the cost of doing that, which is the return on the investments in the engineering, but also then the automation of the monitoring, basically. Yeah, but I think is a great research area that is under investigated.
Agreed. Definitely. Thank you.
Thank you very much. That was a good discussion. There is a question for Timur. It's from Tabajit. He's wondering if your tool only supports Java.
So the tool shared as the artifact only supports Java server runtimes. However, currently we are working towards an implementation for Android, which there's some hoops you have to jump through based on concepts like security, primarily to get that same activity information. Obviously, the battery information is right there, as well as trying to extend it to initially extend it to study TensorFlow and Python. Unfortunately, TensorFlow in Java does not have a very mature API, and so many of the tools that would allow you to really utilize this information don't exist. So one of the big ones is TensorFlow tracing, which is only available in later versions of TensorFlow. And so that's not available in Java, for example. And that means that whatever sampling you have to do has to happen from within the Python runtime or be done on the Python runtime. There are obviously other problems with that, as Python's concurrency model for things like multi-threading and multiprocessing is very different. And so at the point in time where you spin up a new Python process, you ask yourself, what actual language should I run my sampler and monitor in? Because it doesn't really need to be Python if it's a new process. So there's a lot of questions about how you implement that for those systems, but right now that's what we're trying to put together and figure out, is being able to do it completely language agnostically. So modern concepts like things like RPCs, and being able to talk to some sort of daemon-like process that you the developer creates come into play as questions for how to think about that design.
Thank you very much. Tabajit, hopefully that answers your question. So there are no questions here, but I have prepared a couple of, let's say, meta questions that I hope that would be good to start a discussion. And this question is targeted at all the presenters. So one thing that I've always found difficult is showing the value of the work that all of you are doing. Because sustainability, not necessarily, and Rohit said it in his presentation, it doesn't directly tie to dollars. And for example, a lot of you, Elias, for example, is looking for collaborators in industry. And so I wonder if you, especially for people that are trying to do research in this area, perhaps Leo, I don't know, but what is your advice? What is your recommendation? Like, how do you, quote unquote, how do you sell your research to companies, for example, or even to other research to show that it has value?
So it's a little tough, because you're asking someone to consider, do I reduce throughput in order to save on energy right now? And it's not obvious why that's so important. And like, I think all of us highlighted that problem, that how do you quantify and even make a metric for something like sustainability is really, really tough, because there's lots of environmental questions, there's lots of other factors, but one of the things I think is the strongest example is looking at a real world example. So server farms, the biggest cost is cooling. They consume tons and tons of energy. Even if we think about the Bitcoin example where he gave, that is tons of energy that is just taken up for cooling. So what do? We build server farms in Antarctica and in horribly cold places in order to overcome that cost. But having a smart software system and having systems that can do things like energy load balancing as an example of a real application, that changes a lot of the calculus of how much is my server farm actually consuming, because that's very, very different when you actually are able to see, what am I actually doing to maintain this and, well, prevent the computer from lighting on fire, essentially.
I'm going to ask all of the authors, so beware. Elias, do you have any opinion on this?
I can come up with one. I think indeed it's a tough question. I was thinking of the example of Timur, actually, just a stop and think, because I've read that basically one of the ways, for instance, on mobile phones, right? So when you charge your phone, I think it for iPhones, I'm not sure for the Android and other phones, they basically realize that the battery stays longer alive when you charge slowly. So they basically tap into your habit on when to sleep and when to get up, when you put your charger on, and then basically it starts slowly to charge the battery, which actually, I mean, it is again a real world example. I think we have to look into these real world examples of real people that are having real problems with energy consumption. One such problem is the mobile phones now. I think it's a bit kind of well known. Everybody has a little bit of such problem. We all tolerate it, but people would like it if you tell them, we will just increase by 10% the rate or decrease by 10% the rate your battery is depleted. right? So we need to have some kind of, I think, work together with companies, some kind of such small wins that I think the world changes, right? And I think there is an intention from companies. I do believe that there is an intention to become more sustainable. I don't think it's just. I do think that people and let's say the generation of 30-year-olds around the world are sensitive to this. We just don't have the tools. I mean, look at the studies that we do now. I mean, we don't really know how to profile our complex systems in such a way, right? So the intention is there. I think we need to work on the tools, and it doesn't matter to have the perfect sustainability indicator. For me, it matters to have one, because then if you don't have one, you cannot work towards any goal related even remotely to sustainability, right? So these are some random thoughts, I guess.
No, they're random, but they're cohesive.
Yeah.
Rohit, what is your thought? Because you started talking a little bit about this in your presentation.
So again, I'll divide it into two parts. So when we started working on this area, maybe a few years back, this was actually a very big problem that we were facing. So we built certain amount of tools to optimize software system from an energy perspective. But when we go to our downstream partner teams and ask them to adopt the solutions, then this is the exact same problem we were facing. For them, this was not the problem. For them, if you can optimize time, if you can optimize performance, that would be good. But optimizing sustainability, in the current time, they did not have had basically any benefit to it. Okay, unless you are optimizing the software system in a way that, say, it reduces energy consumption in such a way that on-premise data centers energy decreases, and then they save certain amount of money over there. So that was like an easy sell. But only those solutions that could relate to cost in some terms, then only those solutions were sellable. But now what we are witnessing after a couple of years working in this area, because of, say, a lot of discussions around sustainability, a lot of discussions around climate impact, your Paris climate agreements, your sustainable development goals, UN sustainable development goals, because of all of that coming into place, a lot of corporates have a top-down mechanism to implement sustainability now. So a lot of our clients, a lot of our downstream partners have now been mandated to implement sustainability into their projects. And that is why we are now seeing, instead of us running towards the respective downstream partner teams to adopt sustainability in their teams, they're running after us. Do you have something for us? Can we get something from you that can enable sustainability in our teams? So now the situation is slightly different as it was a few years back. So that is what we are witnessing now. And again, selling things now is a slightly easier sell rather than what it was a few years back.
So confirming what Ilya said from the I would say the consulting firm perspective, that is true, that things are changing.
In a sense, yes.
Okay, well, that's a good thing. Stefanos, not to leave you last, but what are your thoughts? How do you sell your work?
Okay, we'll focus on this part by explaining also a simple story. I remember back in 2018, I had a paper accepted in MSR where we compared different programming language and energy consumption. And at that time, we were part of an industrial European project, and we presented our studies at the industry. It were three guys, me with energy efficiency, another guy with the configuration management studies, another guy for security. They received the most questions, but not me, because energy was not important for them. So it was a medium-sized company, a small one. When we're talking about saving energy, I think we should focus on big players. For instance, I will go to someone who's having a huge infrastructure, and maybe they reserving instances from a cloud provider, and maybe they use a specific pay-as-you-go model that actually saving energy could reduce their bills. So in a way to sell my study, I will definitely focus on big players, but using big systems, and small changes can output big savings for them. In a simple way, I would say. Yeah. So,
Ilyas, your comment, is that an agreement comment or a disagreement comment? I can't tell.
I was agreeing until the last sentence whether he was aiming for big wins, but I think I agree, definitely big players, yes, for sure. Yeah, I mean, for sure. You can. They, I think, have exactly. They have, as a previous presenter said, they have, I think, now the top-down somehow initiative to really work on sustainability, like something, and they have to figure what it is and first, and then implement it in processes, and this is where we come. We have a role because we can help them implement those processes and help them in different ways. I mean, we can help them on the process level, on the technical level, on basically understanding what can be done, what needs to be done, etc. But I agree in principle with Stefanos. Yes.
Also, not to be misunderstood, the reason I will go to big players is because they'll be more willing to make this change if I show some evidence. I feel like small companies are not always there. I mean, if I give a solution for mobile device to optimize an application to consume less energy, that maybe hit a jackpot. But something that will run on a server or a desktop, maybe I will not convince them that easily to adopt a solution.
Okay. So if anybody has any comments, feel free to jump in. If not, I have one closing question, and I'll give you a little bit of time to go to the next session. Oh, I guess there's a Stefanos, there's a message for you. So just to I mean, I know that I mean, not all. I mean, Iles was the one that was a little bit different in the sense that he talked about sustainability in a more broader perspective, but the rest of you really focused on energy. And what I'm hearing from you is that how to measure energy is still a challenge. Like it hasn't changed from when I was doing that it was so painful and wrong. Is that correct?
It's
not a consideration for many people. It's not something you think about until you work with it. You know, like another example I can think of. People are familiar with the image processing graph Inception. They made a big upgrade when they changed from the version 1 to version 2 architecture. That was a huge savings because they changed a lot of like the fundamental math to have the same behavior, even though it was a different graph topology. And they know that that's performance savings. But was it energy savings? Because consider that graph now runs on every device. To do image processing, it runs in the backbone of any sort of search engine that's doing reverse image search. I mean, we've talked about mobile devices. I mean, this has a camera. This has lots of image processing, lots of image filters and features like that. But we don't actually know if that new model is impacting the battery life the same way, or if it's even optimized for the lifetime of that device. And even if we're talking about phones, what about IoT devices or any device that works on some sort of federated system? They really need to have very, very low energy consumption. It's really not, because then you can't have many of them, because then they'll just be a burden. So these are questions we're getting tools. Obviously, everyone here is agreeing. We are starting to build those tools, but we're not able to even answer those questions in a way we're happy with quite yet.
I see you're nodding, Iles. Do you agree? We still need better tooling, even though it's improving for measuring energy consumption.
I'm thinking the energy consumption might be hard, but other sustainability dimensions like I don't know, social, it's even more difficult to measure.
Right.
We don't have the tools there. Well, we do have some tools on the technical sustainability now with technical debt indexes, etc. And economic. But the thing is, maybe, you know, when talking about sustainability, we shouldn't also just if we want to be true to the term, right? We shouldn't really just try only to focus on energy consumption, as you said. Yes. Right.
Right. I agree. Okay, and with that, we have come to the end of our session. Thank you all very much. This was very, very interesting. I really liked the discussion that we had. And so that leaves you a little bit of time to go to the next session. Thank you very much for your time. And I hope to see at least some of you in Pittsburgh in 2 weeks. I'll be here waiting for you. Take care.
Thank you all. Bye.
Bye. Bye.
Thank you.